Good afternoon and welcome to this Chemistry World webinar. I'm Ben Valsler, Chemistry World's digital editor. Thank you ever so much for so many of you for joining us. We've got an interesting and fact-packed roughly hour ahead where we're going to look at battery design from chemistry to system. Now, the first thing that we're going to do is let you know a bit about the software that we're using so that you know how to make the most of the webinar itself and how to engage with the webinar. We're using GoToWebinar, and you should notice down one side of your screen, it will vary for everybody's screen. You can move that around however you like. There will be the GoToWebinar panel. And the most important bit in that is for you to be able to put your hand up or for you to ask questions. So the questions box, usually down at the bottom for most people, do just type in any question you have at any point throughout the webinar itself, and we will make sure that we put those to our guest as we go through the webinar. Probably all at the end. If we don't get time to answer all of your questions, or if there's something that needs that special individual touch, then we'll send all of those questions on to our speaker, Ian, and I'm sure he'll be happy to try and get back to you if he's got a good answer for you. Now, if you happen to miss any part of today's webinar or you just want to go back and watch it again, then don't worry, we'll be making a recording available. We'll send that to you in an email shortly, or you can find it at chemistryworld.com/webinars. So anything you miss, you can just go back and watch again. Now, most of today's presentation is actually a software demonstration rather than a PowerPoint presentation. So we don't share slides and that sort of thing. What we will do is just make sure that it's always available to you after the fact so you can go back and watch it as and when you like. So let's get on with the topic of today's webinar. We're looking at battery design from chemistry to system, and by the end of the webinar, hopefully you'll have learned how atomistic modeling can tie battery component performance to chemical structure. We'll learn about collaboration across business units and how that streamlines battery research and development. And we'll learn about the unifying in silico atomistic studies with systemic battery models and how they can predict the performance of new battery materials and cell design. Now, we've been working with our partner, Dassault Systèmes, in order to bring the right topics to you and, importantly, the right people. So big thanks to them for finding such an interesting topic and clearly such an engaging one, and also for helping us find the ideal person to talk to about that. And that is Senior Strategic Technical Specialist Ian Kerman. He leads the Biovia Innovation Centre. He's been there for 10 years, supporting a variety of industries with digitalising their R&D workflows. So he's the right person to know about all of these issues. So the next thing we'll do is hand over to Ian. So hopefully we'll be able to see Ian as well as hear him. Just waiting for him to pop up. And there's Ian. Thank you ever so much for joining us, Ian. It's very kind of you to give up your time today. I shall now step back and hand over to you to carry on with your presentation.
All right, thank you. And thank you everybody for joining us today. As Ben mentioned, we're going to be talking about how the multi-scale modeling going all the way from atoms and molecules to whole battery packs, battery systems can be modeled and simulated, and how that can accelerate your R&D process in battery development. And so the general story that we're going to have for you today is we're going to start off with a market look, so a battery product manager, and how this person can put together information from across multiple sources, be it news sites, scientific journals, things of that nature, to then help guide their decision-making process to figure out sort of what the next step in the battery R&D process should be. Then we're going to get into the battery electrolyte and how we can go from sort of initial screening of additives to doing some Pareto optimization of those, so using some machine learning techniques, how scientific management can be done, so tracking how these additives are being processed, what the results are, that screening process that happens, and then getting into the formulation of those into an actual electrolyte that then can be simulated by a computational chemist. After that electrolyte is simulated, we can then derive certain properties and parameters from those simulations and scale that up to be used in system-wide simulations as well as more mechanical based simulations. And so we'll see sort of how all of these pieces can fit together and how we're doing that at Dassault Systems with our different brands, including Biovia, Simulia, Katia, and others. And so before we start the demo, I'd actually like to first get an idea of what types of battery technologies you guys are currently looking at, what you're investigating, what you're researching. And so I'd like to put up just a quick poll to see sort of what you guys are doing in the lab right now.
Thank you very much. So let's open up the first poll and see where everybody is, see if we're on the same page. So you should hopefully now see the poll question on your screen. All you need to do is tick the boxes for the ones that apply to you. So what best describes your work with battery technologies? So you work with batteries as part of your product design, as modules or packs for use in other products, and battery cells. And the anode, cathode, or the electrolyte, maybe you're working on individual components within a cell, or you're working on batteries in another role entirely. We're going to give you a short while to get your votes in. I can see about 25% of you voted so far, so it'd be good to get that number a little bit higher and see where people are going. So we've already had a couple of questions. Excellent. Thank you ever so much for being so quick off the start point there. We have had somebody who said that they didn't have any sound. That sound may come and go. Unfortunately, it's subject to the vagaries of your internet connection. So if it does go, just give it a short while, it should come back. And if you do miss any part of it, then once again, don't worry. You'll get a video sent to you very soon after the webinar itself. So any bits you did miss, they will be recorded and you can catch up with them again. So let's see how many we've got. Over half of you voted now. I think we'll probably give it a little bit longer. Of course, if you find that you can't really answer any of those, then so be it. Sometimes, again, vagaries of the internet do that to us, but do just pop a comment in the questions box if you like, and obviously any questions that come in there. A couple of comments in there saying anode and cathode already, so there we go. I think that's probably enough people voting now. Let's close down the poll and share the results that we've got. It's a reasonably good spread. We seem to have a lot of people, given we are chemistry world, we quite often work with people who are on the cutting edge doing the molecular design of components. It's probably not a surprise that the majority of people here are working on the anode, cathode, or electrolyte rather than the whole battery for use in other products, for example. So I think that's probably reasonable. Let's, Ian, does that strike you as about right? Is that the balance that you see in the industry as a whole?
Yeah, no, this is especially, given the audience, like you said, this is actually kind of what I was expecting. And I think this is actually a good sign because a lot of what I'll be showing and talking about today is focused primarily on the chemistry side of things. Although we will definitely have something in there for people who are more focused on the battery cells and even the modules or packs. So I think this is going to be a good presentation for the audience.
Excellent. So this should be something for everybody. Okay, well, we will close down the poll results now, Ian, and you may pick up where you left off.
All right, perfect. There we go. All right. So to start the story, as I mentioned, we're going to start off with the product manager. And so using a product from Dassault Systems called the 3D Experience Platform, or 3D Experience as I'll be saying for short, product managers or really anybody can create these dashboard interfaces. And so here we have a couple of RSS feed readers that allow this product manager to collect news stories, information from different sites, different sources, and kind of collate them all into one view. And so, we have different topics for electric vehicle safety, lithium-ion battery safety, and then there's another topic down here. And these are just different RSS feeds. And these can be created from third parties, such as Google or other news sites like that. And so it provides a one-stop place for the product manager to go and sort of keep up to date what's happening in the industry. And so one of the things that is sort of dominating our headlines today, and you've probably heard of yourselves, are lithium-ion batteries catching on fire. So if there's a problem with the battery, or they get overcharged, or something else happens, they can heat up drastically, and this can lead to a cascade of events that causes the battery to catch on fire, burst into flames, etc. Some of these have been very dramatic, as have been seen in the pictures on the dashboard there with the electric vehicles. And so this is something that, as a battery product manager, I want to try to address and try to get ahead of before my company has issues in particular. And so we have this community tool within 3D Experience that allows me to communicate with my team, and we can have a conversation about different ideas to solve these problems, or we can discuss the problems in general and really just have an idea of sort of what we as a team can come together and do. And so what I'm going to do here is I'm just going to create a new post. So let's So I want to just start a new topic of decrease fire risk of our batteries. And I'm just going to quickly tag one of my coworkers, Emma, who is my formulation chemist, and ask her if she can look into sort of adding something or doing something with the electrolyte to mitigate this fire issue. And I'm going to go ahead and publish this. And so when I publish this, what's going to happen is Emma's going to receive a notification that she's been tagged in this, and that's going to lead her to go ahead and respond, and we can pull in other team members and have a discussion where we try to come up with new ideas or come up with a solution, or at least a plan to try and solve this problem. So now I'm going to switch over to the role of Emma. So we're moving along this storyline, and now I'm going to be playing the role of Emma, who is our, as I mentioned, is our formulations chemist. So I received that notification. You can actually see, I have the little notification here showing that I was tagged in a post on Swim. So I can go in there, take a look at it, as I mentioned. And so now I want to get to work. So here I have another dashboard, but in this case, the dashboard, instead of being a collection of different news items in that, instead it's a set of different apps or tools that I use in my daily job. And so here I have this 3D space widget, as we call it. And this is really just kind of a listing of the files that are available on my browser, or sorry, in my server on my platform. And then I have my library screening application over here. And so in here, I could pick a library, I could do a search for a query term, or if I sort of have a pre-composed list of additives that I want to screen, I can just drag and drop that over here, submit this, and now what this is going to do is this is going to take that list and read that list of additives. And it's going to now allow me to analyze and sort of look at what are the property distributions of these different additives. You can see the different compounds with the structures on the right-hand side, along with some properties. I have some histograms here showing me the distribution of those properties. And so this gives me an idea of what my entire library looks at or looks like. Now you can see that there's about 4,000 compounds here. So this is way too many for me to be able to do anything with, to be able to screen or do any kind of formulation with. And so what I want to do is I want to start filtering this down. So one thing I want to do is make sure that the chemical potential is relatively low. I don't want anything in my electrolyte that's going to potentially react with other things in my electrolyte. So I'm going to put this down to about 10. So I've gone from about 3,900 compounds now to about 550. Still too many to work with, but I'm going on the right track here. Next thing I want to take a look at is flashpoint. Obviously, this is something where we're trying to decrease the likelihood of fire, so we want a higher end flashpoint. And so I'm going to set this to say about 350 Kelvin there. And then the next thing I want to do is I'm still at 250, which is still a bit too many. is go through and set a maximum value for my viscosity. Again, I don't want to add this to my electrolyte and have the electrolyte become more viscous, potentially inhibiting or making lithium ion transport more difficult. So I'm going to set this to, say, 2.71, and that brings me down to about 99 compounds. Now, again, these values are all just kind of based on my experience as a chemist. This could maybe be something where we implement some ranking or some machine learning algorithms that might go through and try to pick the best ones for us. But right now, I'm just using my scientific knowledge, my scientific intuition, to sort of gauge what I think good values would be for here. And this gets me down just to a smaller set. Now, I can use Pareto optimization, and what this will do is this will allow me to say how I want these different properties to be optimized, whether I want them to be sort of minimized or maximized, and then it'll give me a set of compounds that are all what are considered equally good. So you can see here I have these different parameters. I can change maximization or minimization. Again, I want to minimize viscosity here. I'm going to go ahead and click submit. And so when this is done running, it then gives me this list of compounds and this property here, or this column called Pareto front. And so if you're not familiar with the idea of Pareto sorting or Pareto optimization, the idea is that all members of the same Pareto front are all equally as good based on your parameters that you set. So the idea here is that I wouldn't be able to, say, decrease my viscosity anymore without maybe increasing another property that I want to sort of keep low. So these are all considered equally good. So I can go in here, search through this until I get to the next Pareto front. So here I have selected all of my first Pareto front compounds, and then I'm going to go ahead and register these. And when I register these, what's going to happen is they're going to go into a project. And this project is going to keep track of all of these additives that I've registered to it. And additionally, it's going to kick off a workflow, a series of workflows on these additives that are going to run additional in silico or additional computational tests on it. And so you can see here we have a heat map that shows all the different compounds that I've that I've registered. It's run these different tests on them. So the tests are on the left-hand side here. The compounds are along the top. And then based on some thresholds that we've put in, these different compounds have either passed or maybe failed these different tests. And again, these are based on thresholds that I, as a scientist, can set and adjust. And then based on whether the compound passed certain tests, it may move on to sort of the next stage in which maybe more expensive or longer computational calculations and simulations occur. And so you can see here, we sort of had a cutoff where we weren't, these compounds didn't move on to the next stage. These 5 compounds then went through these 3 different tests here. And then these last 2 went through and did a coarse lithium diffusion test or a simulation. And so seeing these 2 compounds that have passed this screening stage, I can now go ahead and do my formulation of these. So I'll go into my formulations dashboard. And again, this is just a collection of different tools that I need to be able to do my job here. And so here I have my base formulation. This is just a simple one-to-one EC-EMC formulation mixture, so no other additives in it. And so now what I can do is I can go and clone that. So I'm going to create 4 different clones of it. And now I can start adding those different additives, start adding those different ingredients. So here I have the first one. I'll go ahead and add that as an ingredient. And then let's see. And then this is the second one. So I'll go ahead and add that. All right, and now I can go ahead, enter in just different amounts to be added to the formulation. Again, for the demo purposes, I'm just putting in some simple numbers here. This could be based on sort of my experience as a formulator, knowing that these are kind of the amounts of additives that would have the desired effects without having any undesired effects. We could also, again, implement machine learning here, where we go through, do a design of experiment, and then screen those designs of experiments based on some other measures, and then automatically come up with a set of formulations to run. But I'm just going to do this manually, put these in here. And then again, I'm going to go ahead and register these. And this is going to now go into a new project, a different project. And you can see the little formulation candidates have been added, notification there. And this new project can now be looked at by the simulation chemists and other people who are interested. And so now I'm going to switch roles again. So I'm going to move from being the formulator to now being the lead scientist. So I'm playing the role of Patrick here. I've been assigned to this project as the lead scientist, or the PI, and I've been keeping track of sort of what's been going on with these notifications. So I've seen Emma's done a lot of work here, adding some new candidates to the additive, the electrolyte reformulation, and then added some new formulation candidates as well. And so now I can go ahead, let me minimize that. I can take a look at this project and sort of see where we are. And one thing that happened again is when Emma added those 4 formulations to the project, there was a process that kicked off and started running some coarse grain simulations on that new electrolyte. And it's only coarse grain because it's an automatic process. And so the coarse grain is going to be sort of the fastest running, the least computationally intensive. But it'll give me, as the scientist involved, an idea of whether or not any of these formulations should be moved on to the next stage. And so we can see here, this one formulation, 1536 there, did in fact pass this coarse lithium diffusion simulation. And so what I can do is I can put in a request that this fine simulation be done. And so let me just put in this here. And I'll just copy and paste this. I can put a date. So let's say, I want it to be done by the end of the month. Go ahead, click create. I can confirm that it's a fine electrolyte simulation along with the formulation that I'm interested in. And now this task has been created, and I can go into another tool available on the 3D Experience platform from one of the other brands, Innovia, that allows me to take a look at the simulation. And so you can see there's a handful of different simulations here. This is the one that was just created, appearing at the bottom. I can come in here, I can assign it to somebody. So the computational chemist that I have available for this project is Edouard. So I can go ahead, click that, save that. And now Edward is going to see that project has been assigned to him. He'll get a notification and we'll be able to move on to Edward going on and running the simulation against this formulation. But before we do that, I'd actually like to take another poll and see what types of simulations you are currently running as part of your chemistry process. And so I think there's going to be another poll that comes up.
That's right. Yes, thank you, Ian. It's all fascinating so far, but we'll run the next poll so people can interact. I've got a question to ask while the poll is running as well. So everybody out there, hopefully this time you can see this and interact with this. We're very sorry to the people who couldn't last time, but what type of simulations, if any, do you currently run, either you yourself or as part of your team? Are you running atomistic scale simulations, mesoscale simulations, battery module and or pack simulations, or a completely different type of simulation related to batteries? So we'll give you a couple of minutes in order to get those votes in. Ian, a quick question for you while people are voting though. One thing that immediately strikes me is the efficiency of the way that you can assign things to different people. Do you find that when people adopt this approach, they actually find that they're saving a great deal of time not having to send emails, rely on people reading them, wait for the response, etc., things getting lost in people's inboxes, just because you've got it all on that dashboard and you know exactly who any piece of work is assigned to at any given time?
Yeah, no. So we actually see time savings in a number of different areas. One of which, like you said, is on just not losing emails or not having to sort of wait and respond to an email. Instead, you just get the task right in front of you and you know what to do. The other thing is that because this is all being captured in a single platform, all of this information, all this data, all of these tasks are all being tracked in one sort of central place. And so the advantage there is that not only are you keeping track of sort of who's doing what, but you're also keeping track of all of those results. And so maybe, as an example, I've gone through and I did those additive screenings. I would have information available to me showing, oh, I've used this additive before in these different formulations. Let me go back, take a look at those results and see what I did there, see what the results were, and that can be an additional piece of information to guide my decision-making process in terms of whether or not I want to include that additive in my initial test set. And so this idea of digital continuity, all of the data being stored in a centralized place that's indexable, searchable, and scientifically aware. So where not only are we sort of storing the name of the compound and the compound ID and things like that, but we're storing the structures and we're able to do structure searching. We're able to calculate distances and do on subsequences and things like that. And so there's a lot of that additional advantage that you get of being able to digitize these different processes.
We've just had a comment from Michael Miso, sorry if I'm pronouncing your name incorrectly, who said that when he was not in full screen mode, he could interact with the poll. So if anybody can't interact, that might be the trick there. But I guess, Ian, this also means that when somebody is new to the business or comes into your project, or when somebody leaves for a different role elsewhere, there's a lot less catching up to be done. You don't have to try and talk somebody through or try and dig out all of the emails, because the whole history that you're working on is laid out in the software. You can see who's done what, where we are, what happened before. So if somebody who's new, for want of a less awful management speak word, as an onboarding process, it's so much easier.
Absolutely. And another thing that we've actually heard from some customers is not only does it help with the onboarding, but it also helps with when people leave. So if you have paper notebooks as an example, your scientists might have one or multiple, depending on how long they've been there, maybe dozens of paper notebooks, and really only they know what's in them and how to find their data in there. And so when those people leave, either retiring or something like that, you lose sort of all of that intrinsic knowledge. By capturing this all digitally, you're not losing that information when they leave, because it's already all been indexed, it's all been stored in the platform, in the database, and it's all searchable and findable at that point.
So even though a brand new person fresh out of university hasn't necessarily developed the chemist's intuition yet, they can at least look back and see where that intuition from an experienced chemist led them to go and start to copy it and learn some more. Let's have a
Exactly.
look. I think just about half people have voted now, so let's close this down and share the results. Otherwise, I'm going to be asking you more questions about software for the rest of the presentation. There we go. So mostly atomistic scale, and then with a fairly big chunk for other types of simulation, slightly less for the mid scales and the modules and packs and so on. Again, representative of the sort of thing you've seen before?
This is, yeah.
Excellent. Well, thank you very much, everybody, for completing the poll. We shall close that down now. And once more, we can hand over to Ian to carry on. But do keep your questions coming in. It's only past. There's plenty of time for questions. I can see them coming in at a really good rate. So please keep them in, and we'll put them all to Ian when he's got through the presentation.
All right, great. Thank you. All right, so before the poll, when we left off, we were looking at the lead scientist who had just made a request to his computational chemist to perform a simulation, the fine-grained simulation on that particular electrolyte formulation. And so again, sort of here's where we are in the story, still in the virtual materials lab, but we've moved on to the computational chemist role now. And so if I were to go into my tasks here, let me just refresh my login.
It's good to see he's got security-minded processes in there as well.
Exactly. And this removes any doubt that this is a live demo as opposed to a video. So,
of course.
And so here you can see, here's the task I was just assigned. I have that finish date of May 29th, so I know what the expectation is. I know where, if I have multiple things going on, I know kind of where to prioritize and how to balance things. It's telling me, sort of the fine simulation, the formulation that I want to use. But the other thing I can do is, because I'm a member of this project, I can go back into that same application that the lead scientist was using and take a look at what's been done. So I can come in here, take a look at the course electrolyte simulation results if I wanted to. There's also a task view in here where there might be more information that was added by the lead scientist. If there's specific information about the protocol, all of that will be detailed here, as well as the different candidates, and I can click down into this and get more information about them as needed. But I'm going to move on into my simulation space. And so here I have my simulation launcher. And here's the formulation, the 1536. So I'm just going to, again, drag and drop that over. And this is sort of a easy configuration, if you will. And so I have some pre-assigned temperature settings here. So you can see I can run a simulation for normal operating temperature, or I can do low or high temperature ranges. So if I'm maybe designing a battery and I want to simulate how it's going to perform in the desert, or maybe in cold weather climates, I can simulate those here. I'm just going to go with normal operating temperature. I could have similar selections for the lithium ion concentration settings. I'm just going to do a standard range. I can set the number of replicates I want to run, so the number of simulations I run per setting. So this becomes sort of a permutation of all of these different settings here. The other thing I can do is I can request a battery behavior simulation. And what this is going to do is this is going to create an extra step after all the simulations complete and create a input file to one of our other tools that's going to allow me to simulate how this electrolyte would behave on a system-wide level. And so we'll actually get into that into the next stage. I also have some options here to simulate different degradation parameters, so different amounts of aging or degradation to the battery, so the percentage of lithium that's converted to lithium carbonate, and then the amount of that that's converted to lithium fluoride. I'm just going to simulate a new battery, and I'm going to go ahead and click that. I'll see that the simulation has been submitted, and then I'll start to receive some notifications saying that the simulation has started. And again, because this is a demo, I've sped things up for you here. So you can see here now that the lithium diffusion simulation is complete. In real life, this would have taken several hours, if not a day or more, depending on the type of system you're running. But I can go ahead, click on that, and what this is going to do is bring me to an electronic record, electronic notebook page, if you will, detailing what that simulation was and how that simulation ran and what the results were. So you can see here we have our conductivity and diffusion analysis. We have our raw data here. We have some plots, so you can see here all of the different replicates that were done. And then at the bottom, you can see this configuration file. Now, looking at these results is good, but as a computational chemist, maybe I want to actually go and take a look at that simulation itself. And using the 3D Experience platform and some of the tools available from Biovia, we can do that. Opening it up in Materials Studio, and the simulation, once it comes here, there we go. So I can see the electrolyte in the box. Here we have the lithium ions are the purple spheres, and you can see the different additives. So we have the standard electrolyte, which are these ones here, and then our additive, which if I can get here, which is there. And so I can come in, make sure that the simulation setup looks like it was good. There's nothing sort of out of the ordinary happening. I can run the simulation, or I can play back the simulation here, and again just kind of get a visual idea to make sure that everything looks like it that was supposed to happen did happen. And so this allows me, as a scientist, to have a confidence in the results that are presented here. I could go back, verify the simulation again, and then I can, once I've sort of am happy with these results, I could then let the lead scientist know that that task is complete, which would then move on, or the next task would then be assigned. And so for that, we're actually going to move on now to a new role. And this is going to be our battery systems engineer. And so now we've moved from the virtual materials lab into the virtual systems lab. And so the battery systems engineer received a notification that there was a request for this battery behavior. So this was created once that simulation was completed by Edward in the previous step. Again, because I'm a member of this project, I can go to the simulation. I can take a look at this simulation page here if I wanted. The other thing I can do is, but for what I'm going to do now instead is I'm just going to go ahead and open up my battery behavior tool here. And so this is opening up a different application. It's been pre-configured to load the battery libraries, the battery modules, as well as some of the experiment types or simulation types that I might want to do. I'm going to open up this WLTP simulation here, and you can see kind of how the system simulation is set up. So again, very different from the atomistic simulation we just saw. And so now we're really crossing that scale, going from simulating atoms to now simulating what in essence is an entire electric vehicle here. I can open up the cell. I can see it's been configured with that Materials Studio simulation. And so the electrolyte properties are derived from that electrolyte simulation that was done by Edward in the previous step. And I can, sort of drill down into this further if I wanted to, make changes to the negative electrode, positive electrode, etc. But instead, what I'm going to do is I'm just going to go ahead and start the simulation. And that's going to kick off. And let me switch over to the simulation mode. The simulation, it takes a while to run. And so I'm just going to show you sort of the beginning parts of it, give you an idea of some of the data that you can get out of this, just as an example. And so once this populates on the left-hand side here, all right, there we go. So these are all of the different parameters that are being simulated and monitored in this systems level simulation. So I can take a look at temperature and net. And that's going to give me a comparison, sort of what the increase in temperature is. You can already see there's a slight increase. The scale on the left-hand side gives you an idea. It's not a huge increase, but there is something going on there. I can add a second chart, and in here, I can monitor, for example, the power output as well as the loss of power in the cell. So again, you can see the power output. This would be sort of when the battery is being discharged. In the simulation, there are also recharge examples, which we may get to depending on how long it's able to run for, or we let it run. And we can look at other things here. So for example, I think it was on the power source, we can monitor the voltage of the battery. We can also go ahead and scale this so we can see how the voltage of the battery is changing, and how this correlates, again, to say change in the cell temperature or power output from the cell. And so we can monitor this as we go through the simulation. Again, this is going to take a while to run, so I'm just going to minimize that. We're going to fast forward in time, and we're going to take a look at those results. And so what we have here, let's see. Just go ahead and refresh this page. There we go. All right. So again, I have a tool here that will allow me to drag and drop a baseline file and then a results file. And the idea here is I want to compare my simulation results to a known system with a known electrolyte, known configuration, and compare that to this new system with a new electrolyte. So I'm going to go ahead, just do a search, WLTP. I want to search in the current dashboard. And so this brings me to these two. And so this one here is going to be my baseline. I'll just drag and drop that over. And then this one is my result file. And now when I click submit, it's again going to open up an application that allows me to compare the baseline to my new formulation. And so you can see different parameters here that we're interested in: cell power loss, cell power output, temperature change from initial, so this is our delta T, and then cell voltage change from initial. The blue line here is going to be our baseline, and then the orange line is our test. So this is the simulation that we ran, or is currently kind of running in the background. And some things that I want to look at here: cell power output is going to be the same, so there's no difference in terms of the output. This is kind of a sanity check, if you will, to make sure that the simulation was run the same for both of them. The same simulation was run, so I can make sure I can do a fair comparison between them. And I can see, here there was actually a bit more power loss on the baseline than with the test, so that's an improvement. I can also see that the baseline had about a 1 degree temperature difference, or was 1 degree higher than our test here. And I can actually go ahead and expand this full screen if I want to take a closer look at it. But again, this is telling me that this simulation the simulation with this electrolyte is saying that this is pointing or going in the right direction. And so with this, again, I would go back to that electronic notebook page, and I would add my results to that. And the idea there is we can keep all of the results related to this electrolyte in that one notebook page. So it's all very easily accessible. It's all available to the rest of the team. And it's available to anyone else who comes afterwards who wants to see what type of simulations did we run with this electrolyte? What were the parameters of that simulation? Kind of all of the things that you would do in a typical bench experiment and record in your laboratory notebook, we're actually recording as a electronic lab notebook for our simulations. So now the next stage in this process would be to now take our electrolyte to our virtual test lab. And in here, we're going to do a 3D modeling of our battery module and do a simulation on it to see how the new electrolyte affects heat dissipation. And so let me switch over to our application here. So here you can see we have a battery module with all of our battery cells in here. This is an air-cooled module, and so we have an input port where the air comes in, and then we have an output port where the air flows out. And what I'm going to simulate is a short circuit on this cell here. So the idea is that if there's something that happens to this cell, it short circuits, it's going to discharge all of its energy very quickly as heat. And I want to see first, how is that heat dissipated by the, in the system? And also, does this cause damage to any of the neighboring cells? Because one of the things we really want to make sure doesn't happen is that a problem in one battery cell doesn't lead to a cascading effect or a chain reaction that causes all of its other neighboring cells to fail, which could then cause a cataclysmic event such as the battery catching on fire, exploding, something like that. Again, this simulation would take a really long time to run. And so what I'm going to do instead is just kind of take a look at the results, but I'm going to move on instead to back to the product manager. And so if we go here, as the product manager, so we're on the last phase here, I can take a look at these virtual test lab results and have an indication of what the simulation looked like. So here we can see the playback of the simulation. We have two different ones here. That battery cell in the middle is the one that short-circuited, so you can see it spikes in temperature very quickly and then over time decreases in temperature. There's this particular neighboring cell here. This is the one we're monitoring to see what its cell temperature is. And so if we take a look at this chart here, we can see in the blue line, this is our baseline. So again, we're comparing our baseline formulation to our new formulation. And then this orange line here is our new formulation. And so just taking a look at sort of one point in time at the halfway mark, we can see that there's about a 14-degree difference between the neighboring cell temperatures here. And so this is again pointing favorably towards this electrolyte, either due to its heat conductivity or heat capacitance or something like that, being a better suit for preventing these large-scale battery fires. As a product manager, I have sort of access to other tools and other results. And so, here I can see all of the tests that have been performed as part of the virtual materials lab, virtual performance, virtual test lab. I have access to the project. So if I were interested, I could come in here, take a look at the different additives that were used, et cetera. And then also, on the materials side, I can come in here, take a look at that electronic lab notebook entry that was created, have a playback of the video, take a look at the results from the simulation. So this is a conductivity measurement of the simulation at the different temperatures you can see here. And so with the 3D Experience platform, not only are all of my team members able to really make use of the wide collection of different tools and collaborate with each other. But as a product manager or a lead scientist or principal investigator, it also gives me a tool to keep a high level overview of everything that's happening in my lab on this particular project. And with that, that concludes my demo, and I'm happy to take any questions.
Ian, thank you ever so much. When I introduced you at the beginning of this webinar, I didn't realize that we weren't just getting one person, we were getting a whole team. And you've worn so many different hats and played so many different roles throughout the webinar. It really helps to show the overview of what we've got going on here. We've had lots and lots of questions. Some are very specific, but there are a couple of themes that have emerged. So I'm sorry if I don't mention you by name in particular. Two themes in particular I think we should address first. First of all, what sort of technology are you running this on? Are the simulations run in the cloud on a dedicated server on, an Amazon supercomputer, or maybe just on a laptop? How are you actually running the simulations?
So it kind of depends on the simulation that you're referring to. As an example, this particular simulation here, which is a systems level simulation, this is being run on my laptop. It's not very computationally intensive, and so a laptop is able to do it. On some of the atomistic level simulations, those are a bit more computationally intensive, and so those are being run on a small cluster that we have internal. And then the three-dimensional simulations, the one with the battery module, and we were running the heat simulation, heat dissipation simulation, those were being run on a cloud server that we have. And so the other thing that is interesting to point out here is with this particular platform and with the different ways that you can integrate all of these different technologies, you really do have the opportunity to leverage whatever resources you have available to you. Personally, I've run some of the atomistic simulations and the three-dimensional simulations on my laptop. I usually let it run overnight or maybe over the weekend, but they do run and they will run. But obviously, the more computational resources you have, the faster you're going to get to your results.
So realistically, you can get the results you need with the equipment you already have. If you want to do more complex things and get them done quicker, then it's at that point that you're starting to look at maybe upgrading the technology as well.
Exactly.
The other theme that's emerged from these questions is about whether the simulations are then confirmed against reality, as it were. So at what stage is that process undertaken?
Yeah, so that's actually an excellent point. So everything that I showed in this demo has been virtual or in silico. And so when you transfer the idea to the bench lab, really kind of depends on the scientist, or the lead scientist, the product manager, project manager maybe. But at any point, honestly, we could have switched from doing a in silico screening and simulation to now let's go test these formulations in the lab. Um, you know, there's I showed that one application that had the heat map with all the different the different tests and the additives in that. Um, Sort of alongside those, we were just showing the virtual and the in silico results, but you could also have um, bench experiments as part of that screening process as well. And so in that dashboard, in that heat map, you can have side by side the results of your virtual experiments alongside with your real world experiments. And
Of
then
course, you
same
can.
thing. Oh,
Of course, you can store all of the data from your real experiments in the system as well, so you get that benefit of being able to share instantly and assign them to whoever needs to see them.
exactly.
We have so many questions that I'm actually starting to get lost in them. Let's see if I can pick a couple. So Himanshu Paliwal asks, how are the tools integrated with Material Studio? I think you did use Material Studio at one point. So how do all these different tools integrate together?
Yep. And so that's actually a really good point. And one of the things that I forgot to mention at the beginning, and so I'll mention here. Um, this demo was built as part of the BioVia Innovation Center. And one of the things that we do there is we put together these demos as proof of concepts and in some cases prototypes. And so all of the science and simulations and everything that you saw are real. Some of the integrations and connections on the back end, we've had to do some customization or, some of those might not exist. And so if you were to go and sort of buy or license the BioVia and Simulia suite of tools, you wouldn't have those integrations today. It's something we're working towards, and with every day we're getting closer and closer to that goal, but we're not quite there yet. And so I just want to put that caveat out there. That
So,
being said, the Material Studio integration, a lot of that has been done with another tool called Pipeline Pilot. And so Pipeline Pilot, you can run from Material Studio. You can also run Material Studio from Pipeline Pilot. So it's sort of a two-way integration there. And with Pipeline Pilot, we're able to automate a lot of these processes, a lot of the data conversions, a lot of the data pushing, for example. And so that's how a lot of these connections are being made.
and anyone who regularly attends Chemistry World webinars will remember that we had a webinar about Pipeline Pilot a few years ago now, I think, but that should still be on our website if you want to go back and have a look at that. We had, I'm going to reword this, but essentially we had a question saying, is there a community out there of software users and people who do similar things that we can connect to in order to learn a bit more and to gain from other people's experience? What sort of resources are there out there for people?
So I can talk about sort of on a higher level. So within BioVia, within Dassault, we have a couple support communities that you can join, and on those communities, other users will post questions. A lot of it is sort of, how do I do this, functionality, or I'm having this problem. Is anybody else seeing that? But you could use that as a resource to, hey, I'm running this type of simulation. What parameters did you use, or did you use this force field versus this other force field? You could go there to ask those sorts of questions for sure. That's sort of at the BioVia level. So a lot of that's going to be, and we have a community, one for Material Studio, one for Pipeline Pilot. So they're going to be kind of specific to those products. In terms of a battery community or a battery material community, I'm honestly not aware of one offhand, but that's definitely something that I can look for and ask somebody else in BioVia and get back to you on that.
Okay, but we will make sure we supply all of the questions to you. So if there are things like that where you're happy to help people or able to help people, you'll have their contact details. So thank you to everyone. I think we've got time for one more question, and hopefully I think this can be a fairly quick one. You showed some of the capabilities with regards how you manage the process of a project workflow within a team. And Katarzyna Walczak has asked if there's any possibility to store in the platform articles that the team have written or particular articles that are relevant to the discussion at hand. So can you store additional non sort of database driven things like PDFs of articles?
Yeah, absolutely. So if you remember back in the demo, there were a couple times where I had the 3D space widget on the side. I was dragging and dropping different things from there. In some of those cases, those were actually just Excel files. And so they were Excel files that were either generated by, say, a process that we did. So Pipeline Pilot took the Material Studio results from the simulation, crunched some numbers, and then output a spreadsheet from that. And so you could absolutely store PDFs, documents, other things like that in there. In sort of Dassault, we have another brand that I didn't really feature here called Exelead, and one of their key things is the indexing of and searching of documents. And so with their tools and applications, you could absolutely upload PDFs, documents, Word documents. Those would be indexed and then fully searchable. And there's a couple sort of applications that are on the horizon, scientific intelligence driven, that are purpose built for those types of scenarios.
Perfect. Thank you very much. I'm afraid we have run out of time, but Ian, thank you so much, and thank you to all of the different characters that you've played throughout the course of the last hour. It's been a fascinating webinar. If anybody missed any part of it, we will send you a recording. You can go back and watch that again. Once again, all those questions will be sent over to Ian. So thank you for all of your questions. We really appreciate when people don't just come here to watch, but actually come here to engage with our webinars. And that's what the point of webinars are for. Thank you again for Dassault Systèmes for finding Ian and for finding such an interesting and engaging topic for us to talk about. And that's really it. So we are currently in the middle of doing plenty of webinars for reasons that I think you probably will all have worked out, that people are perhaps spending less time in their office and more happy to spend time doing these sorts of things. So there is a survey as you exit the webinar. It will also be sent to you in the email. We're really keen to know what you thought of this, if it covered what you expected it to cover, and what else we should be talking to you about. So do please fill that in. If you have any other questions or comments, you can email cwwebinars@rsc.org. So once again, thank you to Ian, thank you to Dassault Systèmes. I'm Ben Valsler, Chemistry World's digital editor, and we'll see you for the next Chemistry World webinar.